Example 1.3.6, electricity demand is modeled using a continuous exponential growth function with a demand increase of 4% per year. If the initial demand is 500 gigawatts, find the total energy in joules converted over the next 10 years. The givens from this problem are that it's a continuous exponential function, so we're going to use the equation that the energy or demand in the future is Q0, the initial demand, times the natural number E raised to the power of the growth rate times the number of years. Q equals Q0 e to the alpha t. We were told that the Q0 term is 500 gigawatts, not giga, but gigawatts, if you're a Back to the Future fan. Alpha, the growth rate, we were given as 4% per year, and the time span T was 10 years. And we were supposed to find total energy over a 10-year period. So how are we going to approach this? So what we need to do is think about what a demand curve teaches us. We've got an exponential demand curve. The demand is on the y-axis and the time is on the x-axis. So this is the years of energy usage or electricity usage or demand, and this is the instantaneous power. That's what demand plots as power. So we'll just put this in gigawatts right there. And we know that at the start of the period that we're modeling with this exponential function, we had 500 gigawatts. And this line will tell us how many gigawatts we might use, let's say 10 years in the future. We just come down to 10, we come up, we would find that new value, right? And that's how we would use the line, but the question isn't asking for what the demand will be in the future, it's asking total energy. So what that is asking us to do is integrate this function to calculate the area under the curve there. So the total energy over the 10-year span is the integral from the start time, which in this case is going to be year 0, up to the end time, which is year 10, of the function, the model that we're using, which is given up here. So we need to integrate Q e to the alpha t. I'll just go ahead and plug those numbers in. 500 e to the 9th watts, right? That's a gigawatt is e to the 9th. And then we need to multiply that by e to the alpha. It's 4%, which written as a number is 0.04, or 4 divided by 100. And then we leave the t in the exponential, and then of course we're going to integrate with respect to the time domain t there, dt there. So that gives us our exponential integral. If you want to solve this integral, we can pull out the constant here as the first step, and so that's going to be equal to 500 e to the 9th integral from 0 to 10 years, e to the 0.04 t dt. So we factor out that 500. Since it's a constant, it doesn't affect our integral. Now we just have to know how to integrate e to the ax, essentially, dx, and the answer to that's 1 over a e to the ax. So you look that up in a table of integrals, or maybe you just remember it from calculus, but that's the solution to that integral. So it's going to be 500 e to the 9th. We just apply that to r's. 1 over a, in our case, a is our alpha term, 0.04. Then we just need to multiply by the function again, which was e to the 0.04 t. So that's the integral of that, but we need to evaluate this portion of the integral since it's a definite integral over the values t equals 0 to 10. So we do that and we get 500 e to the ninth. Remember, that's in watts, and we're going to multiply that. We can pull out the 1 over 0.04, and because that just factors out of this term, and then we can say e to the 0.04 times 10 minus e to the 0.04 times 0, year 0. And remember, if I raise e to the 0, I get a value of 1. And so I'm going to end up with 500 e to the ninth over 0.04. So the initial value divided by the growth rate times the function e to the 0.04 times 10 minus 1, which you'll recall from the reading is the formula that was given in the textbook. So that's directly from the text. You don't actually have to perform this integration, although I think it kind of illuminates the problem a little bit. It helps you understand if you follow that math. So then we just need to plug and chug, throw that into your handy dandy TI-89 or favorite online calculator or whatever, and you will find out that the answer here is going to be 6.14781 times 10 to the 12th watt years. So where did that come from? Well, remember what's going to the growth, the exponential here. All of this cancels out. This is 0.04 per year times 10 years, so no units up here. You take the exponential of that, nothing happens with units. So the quantity inside the brackets here is unitless. Over here we have to remember that this is watts over percent per year. Percent is just a number, so we take watts divided by 1 over years and we get watt years is the units here. And that's obviously not what we wanted. We wanted the answer in joules, and so remember, as joules is just a watt per second, so we just need to get rid of this years, and what we'll see is a watt is a joule per second, and then if we convert this over to seconds instead of years, the joules per seconds will cancel out and we will be left with just joules. So to do that, we just need to multiply by 3.154 e to the 7 seconds per year. Right, that's the number of seconds in a single year. Now this year is going to cancel out here, and you should notice by now that the seconds will cancel out in watts, right? The watt is a joule per second, as I said. So and that only goes with joules. So that gives us the final answer of 1.939 e to the 20th joules. So over that 10-year period, that's how many joules of energy will be converted if the demand increases according to the model that we used.